Welcome to our first hydrocarbon, folks, the alkanes, or like I call them, the saturated kings. They're led by hexane Don, a family that's known for its stability and non-reactive nature. Okay, so there's just a slew of examples that we can go over. I mean, from methane to butane, et cetera, et cetera. But the main function is that it's here to basically, alkanes are here to fuel the world. Okay, they're going to provide insulation through waxes. They have a lot of structural components and biological molecules. I mean, the list can go on and on. Okay. The main thing you want to know is that alkanes are saturated hydrocarbons with only carbon-carbon and carbon-hydrogen bonds that are sp3 hybridized. So again, you want to go back to Carbon Man and learning about carbon itself if you do not remember sp3 hybridization. Okay, we went over it briefly there. To name the alkanes, you will follow the rules of naming the organic compounds like we saw before. The only difference is the prefix and the rules you have there are going to be the same. The root and how you actually get the root is going to be the same. The only difference is the ending. The suffix is going to have the ending ane or ane anytime you have an alkane. So we saw an example of that previously, but now we're going to have more examples of those. Now I do have a flashcard moment here, so you can have a flashcard that says alkane on the front, and then a couple of definitions about it, a couple of examples, and then how to name it, and probably a good old example with how to name it. Okay, so keep that in mind. Let's go ahead and get these examples started. So first things first, we know that organic compounds are named with three parts. We have a prefix, we have a root, and we have a suffix. We first want to tackle the root and the suffix, and then we can use the prefix to do that last. Now, of course, you don't have to do it the way I'm telling you. There's so many ways to do the IUPAC name, but this is the way I'm going to be showing you. So in this first compound, the first thing you want to do is find the root. Now, the root means the longest continuous carbon chain. So if I start counting like carbon 1 here, 2, and 3, it's going to truncate it at only 3 carbons. If I go 1, 2, 3, 4, 5 carbons, okay, that's a 5-carbon chain. Let's see if we can get longer than 5 carbons. 1, 2, 3, 4, 5. That's another 5-carbon chain as well. Let's see if we can have any other combinations to get longer. Well, if we did 1, 2, 3, 4, 5, 6, 7, then that gives us the longest continuous chain. So this entire chain will be considered our parent chain or our root. So 7 carbons is going to be hept. Now, the next thing we want to do is figure out our suffix. But the suffix, we're asking ourselves, what family or what group is this actual organic compound a part of? I look here, I see only single bonds. I see only carbon, and carbon-hydrogen bonds. And of course, I'm looking at it, and this is a Lewis structure, but it's also condensed in some parts. So we learned about Lewis, condensed, and skeletal structure, right? Sometimes you're going to see them in condensed, sometimes you see a mixture apparently, and also you will see skeletal as well. So I just have to take it back there. And since I only see single bond, then I know my suffix is going to end with ane. Okay? So the ending of my actual name for this molecule is heptane. Now, we have to consolidate any carbons that are, of course, are substituents or have replaced the hydrogen bond, right? And we see we have 2. One is going to be our CH3. I'm going to get that. There we go. And then we also have another CH3. And these are our substituents that's going to help us understand our prefix. So again, in order to be able to get the prefix and get the name for the prefix, we have to take how many carbons are on or attached to that other carbon. How many carbons are a part of this individual substituent? We only see 1 here. We only see 1 here. So we're dealing with methyl, right? Now, how many methyls do we have? We actually have 2 methyls. So that means we're going to be having dimethyl. Okay, so di is where we're getting that 2 methyl groups here. Now, automatically our name will be dimethylheptane. Are we missing something? Yes, we are. Anytime you have the substituents, you have to give me a location, right? So you give me the name of the group or substituent, give me the location. Give me the name of group, give me the location. So with our methyl groups here, we know that they are on carbon 4. How many do we have? We have 2. So this is going to be 4,4-dimethylheptane. So we got our root, we got our suffix, and we have our prefix. Let's go ahead and do the next one. Again, the goal is to find the longest continuous carbon chain. So if I did 1, 2, 3, 4, 5 here, that's 5 carbons. 1, 2, 3, 4, that's only 4 carbons. 1, 2, 3, 4, that's only 4 carbons. 1, 2, 3, 4, 5, 6. That's going to be 6 carbons. Okay, we also could have counted it 1, 2, 3, 4, 5, 6 on this side. So let's go ahead and choose this one. You could have chosen either one. And let's go ahead and label them. It's carbon 1, 2, 3, 4, 5, and 6. All right, so that means I got my root. It's going to be 6 carbons, so that means I know I'm going to be dealing with hex. Now I see that it's only single bonds, so my ending is going to be ane. Okay, so hexane is going to be the ending of my name. Now I have to deal with the prefix. So I got to figure out what these substituents are. Okay, this substituent is going to be a methyl group. It only has 1 carbon. So we have meth as a prefix, and then it's going to have the suffix YL or il. That's how we got methyl. This one is 2 carbons, so it's going to be ethyl. Now, what is the location? They're both on carbon 3. Now, they're not the same exact constituents that we saw before. So what we do is we have to make sure that everything is going to be in alphabetical order. So here's another layer of information. When you have more than one type of substituent, the way you write it is in alphabetical order. So ethyl or E comes before methyl. Because of that, you're going to write 3-ethyl first. So you're going to have 3-ethyl -3, okay? We have another letter and number here, -methyl. And then, of course, we're going to add our root and suffix here, hexane. So let's figure it out. We got our root, we got our suffix, we have our prefix. Now, with prefixes, again, when you have more than one type of substituent, you have to make sure that you are writing everything in alphabetical order. The only time you have any strange things that can happen is, say you have another CH3 group here. So you have 3-ethyl and then 3,3-dimethyl. The di, tri, or tetra is not a part of the alphabetical portion, okay? So you only want to talk about the substituents themselves, not how many you have. So if you have 5 ethyls or 3 methyls, it doesn't matter. Ethyl is going to come before methyl because you want to do everything in alphabetical order. This goes for all substituents that you can have, no matter the type. You always are going to have them be in alphabetical order, okay? And also, when they are in alphabetical order, we'll see that that's how you actually start numbering things as well, because the ones that are closer to, you want to number the carbons or have the least or the lowest number carbon closer to these substituents, for example. Okay, so that means like, yes, this was carbon 4. No matter how I numbered it, it was always going to be, not carbon 4, sorry. This is carbon 3. No matter how I numbered it, it was always going to be carbon 3 that attached this ethyl and methyl group. Okay, so because it's basically the lowest number, that's the reason why we have 3 here. If this was 2 and 3, or we had an example where we're showing both, then of course I would definitely just have whatever the lowest number is. I would start my numbering of my carbon chain there. Okay. Now, when it comes to alkanes, we do have to add another layer of information, and that is going to be isomers. So as we said before, isomers are going to be compounds that have that same molecular formula, but different properties. And there are going to be 2 types, structural and stereoisomers, okay? So structural is based on different arrangements of bonds. As you can see, there's a 3 carbon here, but the branching is different. So for example, this OH group is attached to this carbon here, whereas this oxygen is right in the middle. Because the oxygen is somewhere different, it gives a completely different structure. And then there's 2 types of stereoisomers. When it comes to alkanes, we're going to be focused on optical isomers and structural isomers. We'll see geometric isomers when we'll deal with alkenes. Okay, folks? But the goal is that when it comes to structural isomers, as we see here, we have 4 carbons. Again, it could be the placement of different halogens, or it could be the branching of the carbons itself. So since we have a straight chain here, and then we have branching here, these are completely 2 different compounds, okay? Different compounds, different function. Next, we also can talk about optical isomers, which are a part of stereoisomers. Stereoisomers are still going to have the same arrangement, but they have different orientations of the groups in space. So it's not just about the structure itself, it's about the orientation of those particular bonds as well. Now, in order for something to be an optical isomer for an alkane, you got to make sure that the carbon that you're focused on is chiral, okay? Little term that you can come up with, and it's going to be chiral. Chiral just means that that carbon has 4 atoms, 4 different atoms. Okay, so let me write all that here. It has 4 different atoms attached to it. Okay, so again, in order for it to be an optical isomer, you have to have a carbon here and have 4 different groups that are going to be attached to it. Okay, folks? You also have to have a molecule and its mirror image. Okay, so here's a mirror image of the right hand. And when you look in the mirror, as you can see, the right hand looks like it's the left hand. But if you were to take both the right hand and the left hand and try to layer them on top of one another with your palms up, guess what? They won't equal to one another. The right hand is going to have a different way where your thumb is, and the left hand is going to have a different orientation of where your thumb is. And those will be considered optical isomers because they're going to have different fingers, of course, and different arrangements. We're talking about our hands here. And it's going to make sure that it has a mirror image that cannot be layered. So you have to have a mirror image that's non-superimposable. So superimposable means layered. So that means if I have my right hand, my left hand palm up, I can't layer them to equal the same mirror image. They actually are different. So you got to have a carbon that has 4 different atoms attached. You have to have a mirror image, and that mirror image is not able to be layered to one another. So even if I was to take this particular molecule that you see here, okay, let me erase this. I was to take this molecule here. As you can see, we have a carbon with that's chiral. It has 4 different atoms attached. There's a mirror image. These are the same. But if you were to layer this one on top of this one, just like the right and left hand, they will be non-superimposable. That makes them an optical isomer. It's also called enantiomer. Sometimes you'll see that name.